So we're at our last chapter, chapter 11, inference on two population parameters. So now we're going to up our game here a little bit by looking at two different samples, if you will, and comparing them as well. We're going to go through these one by one, so I'm just going to leave these here. You can look at them or copy them, whatever you want to do, but we'll get into the learning objectives individually. Our first objective is to distinguish between independent and dependent sampling. A sampling method is independent when an individual selected for one sample does not dictate which individual is to be in the second sample. A sampling method is dependent when an individual selected to be in one sample is used to determine the individual in a second sample. These are often referred to as matched pair samples. It is possible for an individual to be matched against him or herself as well. So let's look at a couple examples that may help you understand this a little better. We're going to look at the examples and decide whether the method is independent or dependent, and then determine the response variable, whether the response variable is qualitative or quantitative. Our first example, Joliet Junior College decided to implement a course redesign of its developmental math programs. Students either enrolled in a traditional lecture format or a lab-based format in which lecture and homework are done using video, and the course management system, MyLab Math. There were 1,200 students enrolled in the traditional lecture format and 300 enrolled in the lab-based format. Once the course ended, the researchers determined whether the student passed the course with an A, B, or C or not. The goal of the study was to determine whether the proportion of students who passed the lab-based format exceeded that of the lecture format. So what do you think? Is it independent or dependent? Here it's independent because the individuals in the lecture format are not related to the individuals in the lab-based format. You might think, well, you would pick the lab, you'd have to pick a lecture base and then as the other one a lab, which would make it some kind of connection, but that's not the case. The response variable is whether the student passed the course or not. Because there are two outcomes, pass or do not pass, the researchers can compare the proportion of students passing the lecture course to those passing the lab-based course. Okay? Let's look at our second example. Are products purchased on Amazon less expensive than those purchased online at Walmart? To answer this question, researchers randomly identified 20 products sold at both stores and determined the selling price at Amazon and the online Walmart store to determine if there was a significant difference in the price of the goods. Here, the sampling method is dependent because once a product is selected at Amazon, the same product has to be selected at the online Walmart store. And in this case, the response variable is price, which is quantitative, not qualitative like the last. Our second objective is to test hypotheses regarding two population proportions from independent samples. Suppose that a simple random sample of size n1 is taken from a population where x1 of the individuals have a specified characteristic. And a simple random sample of size n2 is independently taken from a different population where x2 of the individuals have a specific characteristic. Okay. The sampling distribution of p hat 1 minus p hat 2, and remember p hat is simply the the number that had the characteristic over the total number in the sample, is approximately normal with the mean, which is u p hat or p1 minus p2, which equals p1 minus p2, the proportion there. And their standard deviation, sigma p1 minus p2, is equal to the square root of p1 times the quantity 1 minus p1 over n1 plus p2 times the quantity of 1 minus p2 over n2, and of course all of that is under the square root symbol. And of course, as we've seen all along, provided the sample size is correctly, and there's calculations that you have to do independently on each sample given, that n1 p hat 1 times 1 minus p hat 1 is greater than or equal to 10, excuse me, and then do the same thing with p hat 2. And of course, the sample size has to be less than 5% of the population. If we do that and we have everything, then the standardized version of p hat minus p1, p2, I don't know if I said that right, p hat sub 1 minus p hat sub 2 is then written as z equals the quantity of p hat 1 minus p hat 2 minus the quantity of p1 minus p2 all over the square root of p1 times the quantity of 1 minus p1 over n1 plus p2 times the quantity of 1 minus p2 over n2. And this has an approximate standard normal distribution. The best point estimate of p is called the point pooled estimate of p, denoted p hat, where p hat equals x1 plus x2 over n1 plus n2. In this case, the test statistic for comparing two population proportions is equal to z sub 0, which equals p hat 1 minus p hat 2 over the standard deviation sigma p1 hat minus p2 hat. And you can see the formula here expanded, p1 hat minus p2 hat, all divided by the square root of p hat times 1 minus p hat times the square root of 1 over n1 plus 1 over n2. So we can hypothesis test on two different population proportions, specifically regarding the difference between them. To test hypotheses regarding two population proportions, P1 and P2, we can use the steps that follow, provided that. Now, all of these are similar to what we've seen all along about ensuring that we have a normal distribution or a symmetric curve so that we can make the necessary inferences. Of course, now that we're dealing with two samples, some of the calculations are a little bit different. So the first one is that the samples are independently obtained. Each sample is independently obtained using simple random sampling or through a completely randomized experiment with two levels of treatment. The second one was to ensure that our sample size was large enough, remember, and this was a calculation. Now that we have two sample sizes, it's n1 p hat 1 times the quantity of 1 minus p1 hat is greater than or equal to 10. And we have to do that with the second sample, which is why you have the n2 p2 hat there as well. Okay. And then, of course, our sample size has to be no more than 5% of the population size, and so we have to check both of those samples. And this requirement ensures the independence necessary for such a binomial experiment. So first, let's look at the classical approach, assuming that we just did what we did before and assume that it was approximately normal. Once we've done that, then the first step is to identify our null and alternative hypotheses. And these are really no different than before, except here what we're suggesting the null hypothesis is that P1 would equal P2. And then depending upon which tailed testing we're doing, two-tailed, where they're not equal, left-tailed, where P1 is less than P2, and the right-tailed would be P1 is greater than P2. So these, again, are similar enough that it should make a nice common sense or logical or intuitive leap to these. So these aren't new concepts, just a little bit of different application. Step 2, we're selecting a level of significance alpha depending upon the seriousness of the type 1 error. And step 3, we're calculating the test statistic z naught. And you can see the calculation here where we have p hat 1 minus p hat 2 all over the square root of p hat times 1 minus p hat times the square root of 1 over n1 plus 1 over n2. And where p hat specifically is x1 upper level p-hat with no subscripts is simply x1 plus x2 over n1 plus n2. Okay. Once we have this test statistic z0, then we're going to use table 5 to find the critical value, which of course depends upon which tail test. So remember here in the two-tailed test, our test statistic won't be just the z0, it'll be that z alpha over 2. Okay, in the critical region, it will be our critical value will be negative z alpha, and in our right-tailed test, it will be just positive z alpha. Okay, so once we find the critical region, what we're doing is to see if our test statistic is in those critical regions. And remember that if the test statistic is in the critical region, that's when we reject the null hypothesis. And then, of course, the last part is stating the conclusion. Okay? With the p-value approach, it's again very similar. Step 1 is the same. Step 2 is the same. Even our calculation of the test statistic is the same, except now we're using table 5 to find the p-value, which depends on, again, on which test. Again, we have the two-tailed test where the p-value is the sum of the area in both of these. And so remember what we do there is we just calculate the area from the table that's above z naught, our test statistic, and then multiply that by 2 because we're assuming a normal shape, which would be symmetric, so that the area on both tails would be the same. And the other two, again, the p-value is the area to the left of z naught, and here the area is to the right of z naught. Okay. And so then what we're doing in step 4 is we're comparing the p-value to the significance level, and remember we reject the null if the p-value is less than alpha or the significance level, and of course we then once again state our conclusions. So let's look at an example so we can kind of pull those two different methods together, although they're pretty familiar, although we have some new formulas here. In clinical trials of Nasonex, 3,774 adult and adolescent allergy patients, these are patients 12 years and older, were randomly divided into two groups. The patients in group 1 received 2 milligrams of Nasonex, while the patients in group 2 received a placebo. Of the 2,103 patients in the experimental group, 547 reported headaches as a side effect. Of the 1,671 patients in the controlled group, 368 reported headaches as a side effect. What we're trying to find out is there evidence to conclude that the proportion of Nasonex users who experience headaches as a side effect is greater than the proportion in the control group at the alpha level of significance. So first we have to verify that the requirements are met. Just pulling the data out, we get x of 1 equals 547. This is all given to us. These are the ones who reported headaches out of 2,103 people in the sample. 368 were people from the placebo group that reported headaches, and the placebo group was 1,671. From this, we can calculate p hat 1, which is x1 over n1, which gives us 0.260. P hat 2 is x2 over n2, which gives us 0.220. So now we have to make sure that the sample sizes are appropriate. N1 P1 times 1 minus P1, P hat 1, I should say, is equal to 404, which is greater than 10. N2 P hat 2 times 1 minus P hat 2 is equal to 286.7, which is greater than or equal to 10. So it's also sufficient. And more than 10 million Americans 12 years old or older are allergy sufferers, so both sample sizes are less than 5% of the population size. Since all three requirements are satisfied, we can proceed to follow steps 1 through 5. And the one step I didn't mention, but I highlighted up here, was that the individuals were selected randomly. So let's first try the classical approach. So what we're asking is the proportion of patients taking Nasonex who experience a headache greater than the proportion taking the placebo? So if we let P1 represent those taking Nasonex and P2 represent those taking the placebo, we get a right-tailed hypothesis, with the null hypothesis being that P1 and P2 are equal, that in both groups that they experience the headache at the same proportion. But our alternative hypothesis is those taking Nasonex actually experience more headaches than those taking the placebo, and so that would be P1 over P2. Notice we could also state this as P1 minus P2 equals 0, or P1 minus P2 is greater than 0. The level of significance, since this is a medical kind of connection, is equal to 0.05. So we're looking for a 95% level of confidence. This is not a prescribed medication. This is an over-the-counter, so maybe that's why it's still high, 95, but it's not 99. Okay. In the last exercise that we did, we calculated P hat. I'm sorry, we found P1 hat and P2 hat, and so we used those to find the pooled estimate of P, which is the formula here below, x1 plus x2 over n1 plus n2. Those are the given from the original problem setup. And we calculate the pooled estimate, which is P hat, without a subscript, equaling 0.242. We need this to calculate, we need the pooled estimate because it's part of the calculation for the test statistic. We have each of the individual proportions, P hat 1 and P hat 2, but we also need this pooled estimate, which is the sum of the proportions in the top and the sum of the sample sizes in the bottom. Doing this calculation, we get our test statistic of Z naught equaling 2.85. If we go to table 5 and look for the critical value for alpha equals 0.05. Now remember, this is the critical value at the bottom table. There's actually 3 tables under table 5. We're looking at the small bottom table on the right for a right-tailed experiment with a level of significance of 0.05, and we get that that critical value is 1.645. And here you can see the test statistic 2.85. You can see the critical value of 1.645 in the right area here. And since the test statistic is in the critical region, specifically 2.85 is greater than the critical value in a right test, we reject the null hypothesis. And so we would state this as there is sufficient evidence at the alpha equals 0.05 level of significance to conclude the proportion of individuals 12 years and older taking 200 milligrams of Nasonex who experience headaches is greater than the proportion of the individuals 12 years and older taking a placebo who experience headaches. Yeah, it's really important, like I kind of chuckling at the very specificity of the conclusion. But it really is important that you identify all the indicators and the data points in there so that you're making a very clear and specific conclusion based upon your study. So for the p-value approach, the first few steps are exactly the same as the classical approach. First, we have to verify the sample size as we did. Step 1 is the same, writing the null and the hypothesis statement, figuring out which tail test it is, this level of significance. Step 2 is the same, and we even calculate the test statistic the same way. However, when we go to table 5, what we're looking for is the p-value, and so that's actually the entry in the table for z0 equaling 0.285, and this is the big table here instead of the classical approach when we use the level of significance tables at the bottom. So if we look in the larger table for the z0 score of 2.85, we get 0.9978. But remember that these p-values are the area to the left of that z0 score down here. So that's this area over here, and we're looking for the area to the right of this. So remember, when we have that situation, we have to subtract the value from the table, 0.9978, from 1, because the whole area equals 1, to find the area of the shaded region to the right in the right tail. And so we get that value is 0.0022. Because this p-value is less than the level of significance, 0.0022 is less than 0.05, we therefore reject the null hypothesis and then get the same conclusion as we saw in the last example. So the big difference here is about using that table 5 in different ways. Once you get there, the p-value again is the entrance in the table, and the classical approach uses the level of confidence or level of significance in the tables at the bottom, the smaller tables. Objective number 3 is to construct and interpret confidence intervals for the difference between two population proportions. To construct a 1 minus alpha confidence interval, we must satisfy the same 3 requirements as we did before. Provided that these requirements are met, the confidence interval for P1 minus P2 is given by the lower bound, which is the quantity of P hat 1 minus P hat 2 minus Z alpha over 2 times the square root of P1 times the quantity of 1 minus P hat 1 over N1 plus P hat 2 times 1 minus P hat 2 over N2. And of course, the upper bound is the same formula, but instead of subtracting the second part, the second term, we are adding the second term. So let's look at an example. Constructing a confidence interval for the difference between two population proportions. The Gallup organization surveyed 1,100 adult Americans in 2002 and conducted an independent survey of 1,024 Americans in 2018. In both surveys, they asked the following. Notice they also used the same relative time frame of May. They asked the following question. Right now, do you think the state of moral values in the country as a whole is getting better or getting worse? In 2018, 784 of the 1,024 surveyed responded that it's getting worse, and in 2002, 737 of the 1,100 surveyed that the values are getting worse. We want to construct and interpret a 90% confidence interval for the difference between the two population proportions. So the first thing we have to do is verify the requirements. The samples were obtained independently through a random sample. For the samples 1 and 2, we have these N1, X1, P hat 1, P hat 2, etc. calculations, and so we can see that the figure for the sample size is indeed greater than or equal to 10 for both of these. Okay. Also, the population of adult Americans exceeded 100 million in 2002 and 2018, so the sample size is definitely less than 5% of the population, so all conditions are indeed met. So in order to construct our confidence interval, we just plug in the values of P hat 1 minus P hat 2 minus the alpha over 2 in the rest of the formula and get the lower bound of 0.064. I'm not going to walk through all these steps of entering the data points in here. And then here we see the upper bound using the same factors, but adding them in the second part. So we have a lower bound of 0.064 and an upper bound of 0.128. If we used a TI-84 calculator, you see that we get roughly the same values, 0.064 and 0.128 here for the lower bound and the upper bound. So our interpretation is that we are 90% confident that the difference between the proportion of adult Americans who believed that the state of moral values as a country, in the country as a whole, was getting worse from 2002 to 2018 is between 0.064 and 0.128. If we put this in everyday language, we might say that we are 90% confident that the percentage of adult Americans who believe that the state of moral values in the country as a whole was getting worse increased between 6.4% and 12.8% from 2002 to 2018. The increase between those years was between 6.4% and 12.8%. So that's an important kind of language difference. Because this interval doesn't contain zero, we might conclude that a higher proportion of the country believed that the state of moral values was getting worse in the United States in 2018 than in 2002. Our last objective is to determine the sample size necessary for estimating the difference between two population proportions. The sample size required to obtain a 1 minus alpha confidence interval with a margin of error E is always rounded up to the next integer. The margin of error should always be expressed as a decimal. The formula depends upon if prior values of P and P hat are available, and this is, of course, for both samples. If the prior estimates of P and P hat are available, then we use this first formula where the sample size is the same, n equals n1 equals n2, which equals P hat sub 1 times 1 minus P hat sub 1 plus P hat sub 2 times 1 minus P hat sub 2 times the quantity of Z alpha over 2 divided by E, and that fraction squared. We're looking at this longer formula here. So you use this longer formula if you have prior values from a sample that you're comparing. If you don't have them, then what you use the formula, and again, both sample sizes are going to be the same, and you have just 0.5 times Z alpha over 2 over the error rate E. Let's do a quick example and we'll wrap up this lecture. A nutritionist wants to estimate the difference between the proportion of males and females who consume the USDA's recommended daily intake of calcium. What sample size should be obtained if she wishes the estimate to be within 3 percentage points with a 95% confidence, assuming that A, she uses the results of USDA's 1994 to 1996 Diet and Health Knowledge Survey, according to which 51.1% of males and 75.2% of females consume the USDA's recommended daily intake of calcium. So here we do have prior information, so let's categorize that. Our error rate is 3 percentage points, so that's 0.03. Our Z alpha over 2, we have a 95% confidence interval, so our alpha is 0.05, so alpha over 2, 0.05 over 2 is 0.025, and the Z value, Z sub 0.025 is 1.96, and this is again from table 5, and the smaller table at the bottom, the Z sub alpha over 2 table. From the previous sample, we can see that P1, if we set P1 being the males, we get 0.511 because it's 51.1%, and P2 would be the 0.752, or representing the 75.2% of females who consume. With that, we plug this into that larger formula, we get our p hat 1 times 1 minus p hat 1 plus our p hat 2 times 1 minus p hat 2 times the quantity of z sub alpha over 2, 1.96, divided by our error rate, 0.03 squared. When we do this math, we get 1,862.6. Remember that we have to round up to 1,863, and so the nutritionist must survey 1,863 randomly selected males and the same amount of randomly selected females. What happens if she doesn't have any prior estimates? Well, again, we still have the same variables. It's the same problem. Our error rate is 0.03, our z alpha over 2, etc. And so now all we do is we multiply that z alpha over 2 divided by the error rate squared times 1/2. And what we get is 2,134.2, which of course we're going to round up to 2,135. You always round up. And this gives us that the nutritionist must survey 2,135 randomly selected males and the same number of randomly selected females. So that's the end of our lecture for 11.1.